I made a bad mistake in lecture 8. Remember to fix right away related to why the empty set is open. It is what's called vacuously open, but the reason I gave was wrong. So if you have this, you can go down to the section on topology of the complex plane. We'll make a correction right now. The correction is related to what it means for a set to be open. A set is open if every point in the set is an interior point of the set. So why is the empty set open? I said this last time. It contains all its interior points because it doesn't have any. Well, containing its interior points is not the definition of open. The definition of open is every point is an interior point. So this should really be rephrased. It is still open, but it's open because every point of it is an interior point, and that's a true statement because it doesn't have any points. So the condition for being open, for a set being open, S is open, can be written as a logical implication this way. If X is in S, that implies X is an interior point of S. And if then implication like that is true, if the assumption here, if the if part is false actually, and that's the case with the empty set, given a point in the empty set, it's an interior point because the condition that X is in the empty set is never true. Okay? So it does satisfy this implication vacuously, and that is the reason why the empty set is open, not the reason that I gave last Friday. Okay? So subtle but important. And it was a bad mistake of mine to make. Want to tie up some loose ends in chapter 1? Then we'll do a little bit more fun with mappings. And then after that, we're going to try to do 3 proofs the rest of the class. This is going to be more theoretical again. They are proofs you should be able to do on exam 1.
When is it?
Exam 1, yes, by the way, is 1 week from today. Okay, it's going to cover all of chapter 1 and probably the first 2 or 3 sections of chapter 2. What are some loose ends I want to tie up here in chapter 1? Really just points of emphasis. These are the reading, including the extra reading I gave you. The conjugate operator, Z bar, for a given complex number Z equals A plus I B, is A minus B times I. As a map, taking Z and mapping into Z bar, that reflects across the real axis. I guess I did mention that in class. You should know that conjugation is what you might call linear or operation preserving algebraic structures. With respect to arithmetic, the conjugate of a sum is the sum of the conjugates. The conjugate of a difference is the difference of the conjugates. Those are definitely linearity properties. The ones with respect to multiplication and division you might not call linear, but you'd still call them operation preserving. The conjugate of a product is the product of the conjugates, and the conjugate of a quotient is the quotient of conjugates. Trying to emphasize these things as things you should remember very quickly whenever you need them. Okay, these should be in your mind whenever you might need them. We did mention that the square of the modulus of a complex number is the same as the product of the complex number and its conjugate. And a couple of special cases of that, well, related to that, is that the reciprocal mapping, 1 over z, does equal this. And again, the derivation is to take 1 over z and multiply it by the ratio z bar divided by z bar, and then use the fact that z times z bar is the square root of the modulus. And another particular instance of that fact is when z is I, it should be real quick in your mind whenever you see a 1 over I that's the same as negative I. Negative I is the multiplicative inverse of I. I times negative I is 1. That should be something that you remember very quickly whenever you need it. Something else you should remember is the real and imaginary parts of your complex number can be written in terms of z and z bar. Z plus z bar over 2 is the real part of z, and z minus z bar over 2I is the imaginary part of z, and these are very easy to verify. Just do the arithmetic. Some inequalities that are good to remember are these. The absolute value of the real part of z is less than or equal to, there's a less than or equal to right there, the modulus of z. Same with the absolute value of the imaginary part. That should make good sense if you think about it. You got a complex number in the complex plane. Here's its real part. Here's its imaginary part. The distance between z and the origin is bigger than or equal to the distance between these real and imaginary parts of the origin. Okay, so you can see it pretty clearly from the picture, but it's not too hard to prove symbolically as well. We didn't spend a ton of time with roots, but you should know these facts about roots. Given a complex number z written in polar form as r e to the I theta, and assume this complex number is non-zero, and a positive integer n, there are n distinct solutions of this equation, zeta to the n equals z. They're given by these n distinct numbers here. You take the real nth root of the modulus of z, r is the modulus of z, there. Take e to the I theta divided by n, for example, is going to be 1 nth root. But if you want to get the other ones, add on 2k pi over n in there, where k varies over this finite list of integers. 0, 1, 2, 3, up through n minus 1. If z, the original z happens to equal 1, these things have a name. They're called the nth roots of unity. Unity stands for 1, and are sometimes denoted in this way. Most typically, we take this first one, which by the way is not a w, it's an omega. Omega to equal e to the 2 pi I over n. I'll show you a picture of this in a second. However, in reality, as long as k is relatively prime to n, we can use this for omega and get a generator of this cyclic group. This is a cyclic group of order n. Such values over omega are called primitive nth roots. Geometrically, they're going to form a regular polygon with n vertices in the complex plane, and this code illustrates this. There's n is 1. When n is 2, the two square roots of unity are 1 and negative 1. When n is 3, these are the 3 cube roots of unity. This should be negative 1/2 plus square root of 3 over 2i. Negative 1/2 minus square root of 3 over 2i. You can get these with trigonometry. There are the fourth roots of unity, 1i, negative 1, negative I. Fifth roots, sixth roots, etc. 1 is always an nth root of 1, so you always have a dot there. These are the 11th and 11th roots of 1 there. You can see it's always on the regular polygon. Okay, so you should know those facts. That's a cleaning up of chapter 1, emphasizing things that I didn't really emphasize at the time yet. Let's have a little fun with mappings before we go on to do some theoretical stuff. A little fun with the z-squared mapping. We've looked at how it maps vertical and horizontal lines. I don't know if we did circles with z-squared or not, but what about Lissajous curves? What's a Lissajous curve? Something like that. What's the image of a Lissajous curve like this under the squared mapping? It's something else that's kind of pretty. Okay, these are just for fun. Nothing real deep or significant, just interested in seeing what happens. What if I don't center at the origin? I get sort of an uneven kind of folding going on into the squaring mapping. More on the top than on the bottom. What about epicycles? What's an epicycle? Well, that's kind of a graph that looks like that. What if I apply the squaring mapping to that? Again, it's sort of some sort of interesting folding way. Does this have any applications? I don't know, maybe. Okay. For me, it's just sort of, it's like art, I guess. What about the epicycle not centered at the origin? Again, you get the folding is not symmetric. What about the butterfly curve? That's the butterfly curve. Looks like a butterfly. What are the equations for that? I got these off of Wikipedia, by the way. This is a link to Wikipedia. These are the equations for x and y as functions of t. To get it to look like a butterfly. There's what it looks like under the squaring mapping. It does look like maybe it's some other sort of bug or something, doesn't it? You know, it's a butterfly changing back into some sort of other bug. It doesn't undergoes another, what's it called? Caterpillar. Metamorphosis, yeah. It's like another metamorphosis. What about my wife's Valentine's Day card? I forgot to show you guys my Valentine's Day card. Yeah, well, I'm showing it to you now. It's after Valentine's Day now, and now it's February 20th, 2017. I forgot to show it to you last week. Oh, no, it's not working. What?
It's not Valentine's.
I did enter it. Well, it's sort of showing you there, with some errors. My wife's Valentine's Day card with errors. Little story I tell about this. I made this, I don't know, 8 years ago now or something. And that was my card to her that year. And she's like, this is it? This is my card? And I'm like, I spent 2 hours working on this. So then when she heard that I spent 2 hours working on it, then she was more impressed. Most of the work spent is trying to figure out, you know, where are the points for the word I, which I called EYE and Lynette. Love polar. What if you look at the image of my Valentine's Day card under the squaring mapping? No. Hey, no mistakes on this one. There, it's sideways. I've got mapped I and mapped Lynette. I'm using table and map. You can look up what these do to do that. What about z cubed? We've never done z cubed yet. There are its real and imaginary parts, u and v. What happens to a Lissajous curve under z cubed? Well, it's just more interesting folding. More folding and oh, that's pretty weird. Actually, the animation might be a little bit misleading. Z cubed really is going to take a point and, well, cube its modulus and multiply its angle by 3, its argument by 3, and the animation doesn't make that clear. Maybe if it's not centered at the origin, it can be more clear. Look at the top right, for example. It's definitely going further away from the origin, and it's definitely, the new argument is much bigger than the original. Same kind of thing with epicycles, butterfly curve. Let's look at my Valentine's Day card. Like the cubic graph. Now I think it's upside down. Oh no, it's sideways that way. Oh. Huh. This looks different than the one on my computer. Oh, there it goes. It's just stalled or something. Okay. So just some sort of fun with mappings there. Mappings, again, do have plenty of applications. In fact, they are the heart of a lot of the main applications of complex analysis. Oh, we'll get to those applications later. All right, now we're on to the proofs. What are these proofs going to be related to? They're going to be related to limits and continuity. From the first two proofs, at least. And the third proof, if we have time, is going to be related to topology. So here is the definition of continuity at a point. You got a function and a point. What does it mean to be continuous or continuous at that point? First of all, it has to be defined in the neighborhood of the point. On an open disk centered at the point, so that you can approach the point from any direction. Okay. If you're on a boundary of the domain, you can't approach the point from any direction. So we want to have the topological concept of a neighborhood here to allow ourselves to approach the point from any direction. For all epsilon greater than 0, does there exist a delta greater than 0? So this is true whenever this is true. Let's write these in terms of distances. This fact would be equivalent to saying the distance between f of z and f of z0 is less than epsilon. This is the open disk of radius epsilon centered at this point. And this condition would be equivalent to the absolute value of z minus z0 being less than delta. And with continuity, the function does need to be defined at the point as well. Here's the key equation we're really trying to prove. Okay, so the two examples I want to do this with are the squaring function and the reciprocal function. The one we've done the most with. Let's prove, for example, that the limit as x goes to O, I'm going to use the complex number 3 plus 4i in both of these examples. 3 plus 4i of z squared is, what would it be? Well, this function is continuous. We're going to prove it's continuous at this one point. Knowing ahead of time that it's continuous, I can hypothesize that it's going to converge to the square of that number. Let's go ahead and write that in here. 3 plus 4i squared. If you square that out with FOIL, first times first is 3 times 3 is 9. Last times last is 4i times 4i is negative 16. 9 minus 16 is negative 7. And the outside and inside products give you 12i and then another 12i. 3 times 4i, we're going to get 24i. That's what the limit should be. How do you prove it? It's good with these kinds of proofs to do some scratch work. Okay? Practically nobody can write a beautiful proof of something like this without doing some scratch work. Okay, I can't. And I make the emphasis on the word beautiful. You're going to see why this proof might be beautiful than more beautiful than some other proof. The key thing is you want to look at the expression that is the distance between f of z, and in this case f of z0, which is negative 7 plus 24i. If your function didn't happen to be continuous or even defined at z0, it's still possible for the limit to exist, but it would not equal f of z0. I write that down, the function and the value of the limit in absolute values like this, and I think to myself, I'd like to make this expression small. How small? Smaller than any given epsilon, no matter how small epsilon is. As long as z is sufficiently close to z0 within delta of it. z0 in this case being 3 plus 4i. And I think in the complex case, this seems especially difficult because you look at this kind of thing and it's like, well, what in the world do I do with this? Well, it's going to turn out that this can be factored, but not in an obvious way. You got to think about it a little bit. Think in terms of square roots of -7 plus 24i. We already know one square root of it. So 3 plus 4i squared is -7 plus 24i. One square root is 3 plus 4i. But every non-zero complex numbers has 2 square roots. And in fact, they do have to lie on a polygon centered at the origin, just like the roots of unity do. Although this is a degenerate polygon, when you have 2 of them, they are going to be reflections of each other across the origin here. Three plus 4i and -3 minus 4i should be what we're after. They should allow us to factor it like this. Now, this is definitely worth checking. Is this really true? Is this the product of these two factors really equal to this? It's not obvious. Let's try checking it. So this checking is part of my scratch work. It's not part of the proof here. FOIL is z squared. This first times first. Outside times outside is z times this with the minus sign distributed through. That's going to be plus 3 plus 4i z. Inside times inside. Product of these two with the minus sign distributed through is going to be, or actually I can have the minus sign right here, as it is. The outside and the inside terms are going to cancel. This completely cancels with that. Last times last, plus 3 plus 4i times -3 minus 4i. Now that's not the complex conjugate of that. You shouldn't expect to get a real number in this product, and we don't want a real number, we want that. Isn't that? 3 times -3 is -9. 3 times -4 and 4i, and 4i times -3 is going to give us minus 24i, and then last times last is going to give us plus 16. Oops, did this not work out? Actually, it is working out. This does equal 7 minus 24i, which is what I get when I distribute the minus sign through here. So that's the same as -7 plus 24i. It's the same difference. So it's good, right? You don't see any mistakes? Good to you? Why is this helpful? Why did I do this? Probably should have said that right away. I'd like to, again, to make this small, smaller than any given epsilon, by choosing z sufficiently close to 3 plus 4i. By making this part small. Should probably have extra parentheses in here. By making this part small. But what about this part? Is that small? If I'm close to 3 plus 4i? It's not arbitrarily small, at least. So how do I deal with that? Focus on this expression here, and let me go ahead and put the minus sign through. This cannot be made arbitrarily small if z is arbitrarily close to 3 plus 4i, but it can't get too big either if z is close to 3 plus 4i. can I put a bound on how big it can be? And if I can, that's going to be good enough. This is, for example, definitely less than 10 when z is within, say, 1 unit of distance from 3 plus 4i. Then this would be less than 10, and this could be made arbitrarily small. And that's going to lead me to finishing the proof if I can do that. Is 10 the answer? No, probably not here. Well, without loss of generality, have we done W log in algebraic structures? Without loss of generality for those who are unfamiliar. This is an abbreviation for without loss of generality. We can assume z is close to 3 plus 4i. Say less than 1 unit away, just to pick a nice number. What would that assumption tell us about this expression? Well, through a little trickery, you could write that expression this way. Like that. A little bit of trickery. Adding 0 in a convenient way. 3 plus 4i minus 3 plus 4i. It's a little extra tricky in the complex case compared to the real case. These two things are equal. Right? They simplify to the same thing. And this one's nicer to work with in terms of the assumption we're making here, because this part's going to be less than or equal to that, or strictly less than 1. And by the triangle inequality, here's our first application of the triangle inequality. This is less than or equal to this plus this. Right? What does the triangle inequality say? It says, in its simplest form, the modulus of z1 plus z2 is less than or equal to the modulus of z1 plus the modulus of z2. I'm applying that here, and right here, with this thing playing the role of z1, and this thing playing the role of z2. And now my assumption, without loss of generality assumption, is going to say this is less than 1 plus whatever the modulus of that is, 6 plus 8i, the modulus of that is square root of 100 is 10. Hey, I was close with my guess, right? I guessed 10, but it turned out to be 11. This is definitely tricky. I mean, not only dealing with the epsilons and deltas, but tricky algebra. More tricky than it is in real analysis. We're dealing with the extra complication of complex numbers. This factoring was definitely tricky. Probably, even though I'm saying you could be responsible for this on a test, I maybe help you to some degree with, for example, realizing this. But you should certainly on your own try at least one other example like this. And I'm realizing this is taking so long, I think we're going to maybe not do as many proofs today as I was hoping. Because it just takes a while for this to sink in, and I hope you're able to pay attention well enough. Let's do the full proof now. Let's do it in a nice break. Get down. This is just scratch work so far. Well, I suppose I should finish the scratch work, so to speak. Not really finish with it. Ultimately, because of this fact, this is ultimately less than 11. We're going to be able to say this is less than 11 times the modulus of z minus 3 plus 4i. And if you choose delta, delta is the measure of how close z should be to z0, to be, say, epsilon over 11, This is going to be less than delta, and if delta is equal to, say, epsilon over 11, that's going to mean this whole thing is less than 11 times epsilon over 11. Can you see this okay? No?
Like, not really, no.
11 times epsilon over 11, which is epsilon. Let's put it together. Hopefully it'll make more sense if we put it together now in a nice proof. Again, remind yourself of what you're trying to do. You're trying to show that the output of the function, z squared, can be made arbitrarily close within a given epsilon of that thing by taking z, and why did I put an x there? That would be 70. By taking z sufficiently close to 3 plus 4i. Within delta, where delta is the measure that's sufficiently close. You always start these proofs by saying, let epsilon greater than 0 be given. I call it the stamp. Actually, I got that from Dr. Wetzel. Pretend you got ink and you got a stamp, and the stamp says, let epsilon greater than 0 be given. Get the ink on your stamp, bam, goes right there, the first sentence of your proof for these kinds of proofs. Epsilon's an arbitrary positive number. Doesn't matter how small. I could add the phrase no matter how small. It's not logically necessary. I'm imagining it to be small. And then you do kind of a funny thing in the next sentence. You choose your delta right away. And if somebody's reading this proof for the first time, they're like, what? Where'd you get the delta? But you know the scratch work. You choose delta based on the scratch work. I want delta to be, well, certainly less than or equal to epsilon over 11 based on the scratch work. But also, based on this without loss of generality, less than or equal to 1. Choose delta to be the smaller, the minimum of 1 and epsilon over 11. And it is worth noting that that is positive. Since epsilon is positive. The next step is to assume that the distance between z and z0, which is 3 plus 4i, is less than delta. That's an assumption you make. We're going to assume z is this close to z0. When you're doing a pure limit problem, not related to continuity, you also assume this distance is bigger than 0. You assume z is not equal to z0. And sometimes that's a necessary assumption, not really here because the function is continuous. But we're doing really a continuity proof with limits. And so we are, z definitely could equal 3 plus 4i. Probably what's good to do next is to do the without loss of generality, the calculation we did related to that. And we ultimately use the triangle inequality, so in our sentence structure for our proof, it probably would be good to next say, by the triangle inequality, you can write out the words triangle inequality. You can also use this shorthand. But realize when you use that shorthand in a proof like this, that's not delta is not equal to. It's triangle inequality. Okay? I'm okay with abbreviations in proofs, as long as they're standard abbreviations. Such that for such that, ST for such that, backward Z for there exists, upside down A for all. This for triangle inequality. Okay? We like to save time, but do put things in a second structure. By the triangle inequality, what should I write down? Essentially what I have here, without loss of generality part. That's more for the scratch work. The absolute value, the modulus of z plus 3 plus 4i. By algebra, you don't need to say by algebra. is the modulus of z minus 3 plus 4i, say in parentheses, then plus 6 plus 8i, just really adding 0 in a convenient way. And now the triangle inequality comes into place to say this is less than or equal to the modulus of z minus 3 plus 4i in parentheses plus the modulus of 6 plus 8i. This modulus, by assumption, is less than 1, and this calculates to 10, so we get our 11 here. I'm assuming the distance between z and 3 plus 4i is less than delta, and delta was defined to be the smaller of 1 epsilon over 11. So delta definitely is less than or equal to 11, or excuse me, 1, which I guess means I should have a less than or equal to here instead. I'll just strip less than. Where are we trying to go with this? We're trying to go back to the beginning of the scratch work to the end here. Now work with this thing. It might be good to say the factoring fact first. Since z squared minus, in parentheses, negative 7 plus 24i can be factored as z minus 3 plus 4i in parentheses times z minus negative 3 minus 4i in parentheses, you'd be trusting. You should check if this is right. If you factored wrong, then that would be wrong, and the proof would be invalid. So we are trusting that this is right. We did check it over here. Since this is true, we have that the modulus of f of z minus negative 7 plus 24i, which is the same as the modulus of z squared minus, in parentheses, negative 7 plus 24i, equals, really you can take this as, it's the modulus of this product, which is the same as the product of the moduli. Let me write it this way. Let me go ahead and distribute the minus sign through there and write that one like this. Just to make it look a little prettier. It's convenient to rearrange it like that. And then use the fact that we just derived from the triangle inequality to say this is less than or equal to 11 times this, but that, okay, let me go ahead and write that. That, by assumption, is less than delta, and delta is less than or equal to epsilon over 11. So this simplifies down to an epsilon at the very end, which is what makes the proof pretty, once you've acquired the taste for it at least. We did what we logically needed to do. I didn't phrase it in terms of open disks. I could have. Give me an arbitrary epsilon. That's going to be the measure of how close I want to be to 3 plus 4i. Excuse me. Negative 7 plus 24i. I'm going to choose my measure of how close z needs to be to 3 plus 4i. I'm going to do some work that came from my scratch work that's going to help me finish the proof. This also helps me up here. Here's the conclusion part. This is where we show that the distance between the output and the outputs of the function when z is close to 3 plus 4i and this number are going to be within epsilon of each other. That's algebra. This is algebra based on this fact. This is less than or equal to 11, so we get 11 times. This is the modulus of z minus 3 plus 4i in parentheses. But that, by assumption, is less than delta. And the way delta is constructed it's less than or equal to epsilon over 11, so we get an epsilon at the end. Mathematicians usually put QED at the end of proofs. Many Christian mathematicians, including myself, put PTL. Praise the Lord. At the end of proofs. Okay. How long did that take? About 25, 30 minutes? I'm not going to be able to do 3 proofs today. Can we do 2? Let's try a second one. And let's make it a similar type as this, except change it to the reciprocal function. And again, what you're really proving in proving these limits is you're proving the continuity of these functions at the given point, because you're proving the limit of the function equals the function value at that point. I hope you can do that calculation in your head pretty fast. I mean, it turns out nice 25 there on the bottom, because the modulus 3 plus 4i is going to be 5. And that's the square of the modulus. We'll try to go faster, see if we can finish here in 15 minutes from now. Okay, what about the scratch work? Okay, I look at this expression. There's my function. There's my limiting value that I'm trying to prove. Is the limiting value. I say to myself, I'd like to make this small, less than any given epsilon, by making z sufficiently close to 3 plus 4i. Once again, you kind of look at this and like, well, what do I do with it? And oftentimes, you kind of just do the only thing you can do. In this case, subtract the fractions. You get a common denominator of 25z. Be careful not to make mistakes. That looks good. But now, I mean, I could multiply the z through, and I could also distribute the minus sign through, but is that helpful? It's not clear that that's helpful. And actually, what is most helpful here is something unexpected, perhaps. And that, in the top here, is to factor out the 3 minus 4i. Why is that helpful? Why did I know to do that? Because I'm trying to, again, make this smaller than a given epsilon by taking z sufficiently close to 3 plus 4i. I know that 3 minus 4i is the conjugate of 3 plus 4i, so their product is the square of the modulus of z of 3 plus 4i. So if I factor out a 3 minus 4i here, to get a 25 there, I'm going to need a 3 plus 4i right there. And that's good, because now I have something that is related to z minus, in parentheses, 3 plus 4i. That thing in reverse. And I can make that thing as small as I like by taking z sufficiently close to 3 plus 4i. This is good. It's definitely not obvious that that's the trick to do. It's a tricky trick as far as tricks go. But what about the z down there? Can we see that z down there? Okay. What about the z down there? Is that causing trouble for us? If that's small, this could be big. But is z small? Well, z is getting close to 3 plus 4i, so it's relatively close to the origin, but it's not arbitrarily close to 0. this is not going to get too small, meaning the fraction can't get too big. And, okay, we can do it without lots of generality here. Once again, we can assume the distance between z and 3 plus 4i is less than 1. As far as showing that this can't get too small, it'll be good enough here, I think, for us to just rely on a picture, which, technically speaking, we shouldn't do on curves. But I think for today, it's good enough, good enough. Where is 3 plus 4i? It's right there. I'm within 1 unit of distance from 3 plus 4i when I assume this, which means I am more than a certain distance from the origin. I'm more than the distance between this point and the origin right there, away from the origin. In particular, to keep it simple, I'm more than 1 unit away from the origin. And we'll be satisfied with the picture to see that in this case. So z itself is more than 1 unit away from the origin, which means its reciprocal, 1 over the modulus of z, is less than 1. And that's going to be handy here. This is now going to help us say that this is less than the modulus of 3 minus 4i over 25 times the modulus of, I can switch around the order, z minus 3 plus 4i in parentheses. It's okay to switch around the order because I'm taking the modulus.
So you took the z out because it's going to be less than 1?
Yeah, because 1 of the modulus of z is less than 1. That's why I can write a less than sign there. I'm really using the fact that the modulus of a quotient, you can take the quotient of the moduli, and I'm using that fact without saying it. That's probably another fact that I should have put on there, clean up from chapter 1. I probably should have done that. The modulus of a quotient is the quotient of the moduli. I'm using that there too. And the modulus of this is simple. It's what? 1/5. Modulus of 3 minus 4i is 5. Modulus of 25 is 25. This is 1/5 times the distance between z and 3 plus 4i. I want this to be less than epsilon by choosing z sufficiently close to 3 plus 4i. If delta happens to be less than epsilon over, well, even 5 epsilons make it nice, then the 5's will cancel, and this will be less than epsilon. Okay, let's do the proof, and again, hopefully the proof will make it a little bit more clear. The proof is logical, things in the right order. The scratch work is scratch work. It's stuff all over the place. Let epsilon greater than 0 be given. Is your stamp? Boom. Choose delta to be the smaller of 1 and 5 epsilon. And once again, if you're reading this proof without looking at the scratch work or without thinking about the scratch work, it's like, what? Why did the author do that? The author had their scratch work. That's why. And it worked out nice. We are once again going to assume z is within delta of 3 plus 4i. I'm not going to use the triangle inequality here. I'm going to rely on a picture. So this is not really a rigorous proof. Not completely rigorous. Proof. let me just say so that the modulus of z is bigger than 1 and 1 over the modulus of z is less than 1. And the reason for the so that is the picture. That's why this is not a completely rigorous proof. Proving that this is true might be a bit tricky. So that's why I'm avoiding the fully rigorous proof. Then, it might be worth saying some algebra here. Saying this algebra that you can, when you factor out 3 minus 4i out of here, that you get this. That might be worth saying. This makes sense. Fact. Not that you're always going to have a sense fact that you use, but in these cases we do. Since 25 minus, in parentheses, 3 minus 4iz equals 3 minus 4i times, in parentheses, 3 plus 4i minus z, we have that the modulus of f of z minus 3 minus 4i over 25, that's the value of our limit, is the same as the modulus of 1 over z minus 3 minus 4i over 25. Now we're just still doing algebra. This equals getting the common denominator of 25z, the modulus of 25 minus 3 minus 4i in parentheses times z over 25z. Now we use the fact that it was in the sense. Let me go ahead and put the moduli in top and bottom individually. Let me go ahead and use this fact that's up here. This is the modulus of 3 minus 4i. I guess I'm going to need another fact, but the modulus of a product is the product of the moduli. Don't need a modulus around 25 because it is its own modulus. And modulus of 3 minus 4i again is 5. 5 over 25 is 1/5. And again, 1 over the modulus of z is less than 1, so you can say this is less than 1/5 times the modulus of z minus 3 plus 4i, which I'm assuming is less than delta. But delta is less than or equal to 5 epsilon. So I get an epsilon here at the end, PTL. Yeah, it took about 13, 14 minutes. That was pretty quick. All right, so again, assuming this is true just from the picture. To keep things simpler. I'll think about a fully rigorous proof after class here. Maybe I'll just send you a note about it. I was also going to show today that open disks are open sets. But we don't have the time for that. Open disks don't include the boundaries, so they should be open sets. But to prove that they are an open set, we have to prove that every point of an open disk is an interior point of the open disk, and it is a little tricky. We don't have time for that. Let me just spend 2 minutes briefly talking about linear approximation again. Next time on Wednesday, in addition to perhaps doing the proof related to showing open disks are open, we are going to focus on the derivative more, and what it means for a complex function to be differentiable. And even more important than differentiable is a related concept of a complex value function being analytic. Section 2.3, the title is analyticity. Very much related concepts, but analytic is a little stronger kind of concept and more important in the big scheme of things. let me just say that in, again, you should read this stuff on your own here, what I have here. The example here is the squaring function. And the point that I'm taking the derivative at is 2 plus I. And we're thinking in terms of linear approximation. I showed you this last time, but the main thing I want to emphasize about it today is that so what are we looking at here again? Essentially, as the lambda slider goes from 0 to 1, we're going from the domain region that we are thinking about finding the image of to the actual image. And as the domain region gets smaller, the image of the function z squared, which is the pink region here, and its linear approximation, the blue square here, or rectangle, get closer and closer together as the original set that you were finding the image of gets smaller. What I want to say today that's slightly extra compared to what I said last Friday about this is that with complex, this kind of thing is going to happen with complex differentiable functions, that you get linear approximations like this. But those linear approximations are of a very special form for these complex functions that don't apply in general to the corresponding real planar mapping. We've been emphasizing the correspondence between a given complex mapping of the complex plane to itself, having a corresponding real planar mapping from R2 to itself. And we basically, geometrically speaking, have treated these things as equivalent. In terms of linear approximations, for the planar mapping, the real planar mapping, you can, as long as your function is nice, you can always do linear approximations using Jacobian matrices. For the complex planar mappings, where the complex mapping is differentiable and ultimately analytic, the corresponding linear approximation takes on a special form. It's not just any old linear approximation that works. The complex function special form requires that the Jacobian matrix that helps us find the linear approximation is of a special form. Okay, that's all I want to say for today. We'll get into more details of that on Wednesday. See you then.